very good question. You know, sometimes you feel that there are some questions that would be very expected to show up in the exam. This is one of them. The trusts would be there because they are very good for the multiple choices, really, which is the format of the exam. So it says identify the zero force members in the trust and determine the force is a member KJ. So let me just highlight those members probably just for the sake of. All right, so KJ is here, KD is here, and CD, which is here, all right, of the path trust, which is this type of trust. State if the members are in tension or compression, use method sections. Also, it says determine the forcing member GH, all right, and GF here using method of joint. So, all right, so we want to, it is like a true example. It has everything: zero force members, method of joints, method of sections. All right. So can anybody tell me where are the zero force members first? You can type actually as well. You can talk or type, either ways. Anybody see any zero force members in this structure? IE, all right. Anyone else? All right, so let's look at it. So look at this HF guy. So look at EF and FG are collinear, right? EF and FG are collinear, correct? They are in the same line. No external forces at F, and the third member is connected to this common joint, right? Does that make sense that HF to be equal to 0 using the law 2? It is 0. Because EF, FG, collinear, HF coming to that. No external force. So it has to be equal to 0. All right. Also look at this one. KJ and JI, collinear, right? KJ and JI collinear. No external force coming to the J, but third member is coming there. So the third member is 0, again, losing the same law. KJ, JI, DJ coming to that. So I'm going to say JD, again, law number 2, it is equal to 0. All right, so this guy and this guy are 0. All right, and I do not see any other force to be 0 really here. That's it. All right. Now that we understood what are the zero force members, let's just find the first problem. The first problem says that KJ, KD, and CD forces, right? Method of section. You know that method of section already. You know that you can cut like this. It would be very good because all three really ask, so it would be perfect for this one. But before cutting, even I'm going to erase this, I'm going to tell you, you need to find support reactions. Why we need to find the support reaction? Because if I cut, select left or right, I'm going to look at one reaction either ways. Let me show you the reactions. This is GY, this is AY, and this is AX, right? So when I cut from here, I'm going to select left or right. That's the procedure, right? But you're going to see the cut section, the support. Even if you select left or right, doesn't matter. So we need to find it. There is no way out of it. We need to find the support reactions. So let's find the support reactions first. All right. Summation of forces in x direction equal to 0. This direction positive, negative AX. No other horizontal force equal to 0 from this AX is 0. Summation of moment about point A, for example, equal to 0. So summation of mode about this point, these two guys wouldn't be appearing in the equation. The only unknown left would be gy. So we can find it. So starting from the gy itself, as you can see, gy rotating counterclockwise, so positive. The arm for that would be 1, 2, 3, 4, 5, 6. 2 would be 12 meters. And then you have this 40 guy clockwise, negative. The arm for that would be 1, 2, 3, 6 meters. And then we have this 30 clockwise again. And it would be the lengths would be 1, 2 would be 4 meters. And then we have 20 guys and 22 meters arm for it. Nothing else, equal to 0. From this, your gy would be equal to, so let's see, gy would be, so 20 times 2 plus 30 times 4 plus 40 times 6 over 12 would be 33.3 kilonewton. Okay. And summation of force in y direction equal to 0. This direction positive. We have ay, we have negative 20, we have negative 30, we have negative 40, we have positive gy, nothing else equal to 0. Gy we have found to be 33.3. From this, the ay would be equal to 56.7. All right. Okay. So these are your reactions. This one is 33.3. This one is 56.7. So now we can cut. I'm gonna cut from here. So when you cut, you can either select the left or right side. So I don't know. I mean, it doesn't matter really. Probably I just should show both of them actually at the bottom. So shall I erase the support reactions? Any question, the support reaction calculations? All right. So what I'm gonna do, I'm gonna erase this portion. All right. So I'm gonna show you the so if I want to show the other side. All right. So this is J, this is D, I, H, G, F, E. All right. So let's just show the reactions here. Here is AY that we have found to be 56.7. Here you have the 20. Here you have the 30. Here you have the 40. Here you have the 33.3. All right. Here you have these three forces as a result of cut. So this one is TKJ. This is TKD. This is TCD. All right. One thing you want to pay attention here is that this inclined force, inclined member, KD. All right. You don't know this phi angle, but you can create a triangle ratios on this. How you can create? You can say there is a triangle here, right? With the height of 3, with the length of 2. Very similar to something we have learned before that we can do. You can create a triangle, right? 3, 2. It's the same thing here. 3, 2. And the hypotenuse would be what? Would be 3 squared plus 4 to the power of half. Would be 3.6. Okay? So you can create your own triangle because what you need is a ratio. Only ratios of this triangle is important for you. You don't have to go with, well, you can use the full, basically height and full lengths because you need the ratio of them really. All right. So we have everything for using in finding these unknowns, these 3 unknowns. So what you can do. So you can either select left or right side. I don't know, just select the left side, for example. I'm going to select the left side. Okay. So what you having here? So you need to now be a little bit just like this, I would say street smart and see, all right, which equation would be helping you the best to find the unknowns. For example, here you're having this TKS, right? And here you're having this TKD, all right? So I would say summation of moment about point K would be good. Summation of moment about point K would be good here because these two would be gone, so you can find this one from here. So summation of moment about point K equal to 0. This direction positive. So what forces do you have? You have this TCD and 3 meters is the height, right? So it would be TCD times 3 meters. Okay. These two guys wouldn't appear in your equation. Then you have what? You have this guy, 30, it is clockwise. So 2 and 2 would be 4. So each of these guys is 2, right? Okay. This one also clockwise. All right, this force wouldn't produce anything. Sorry. Oh, so we're finding the summation moment of point K, my bad. If it is point K, this is correct, but 30 wouldn't produce anything. So let me just erase this portion. Sorry. All right, about point K. So this 30 wouldn't produce anything. This 20 would be counterclockwise with the arm of 2. And then we have this guy rotating clockwise, so negative 56.7. The arm for that would be 2 and 2, 4. All right, nothing else, equal to 0. From this TCD would be equal to, all right, here we would say 40 minus 56.7 times 4. So it would be over 3, would be 62. 62.27 more than 0, so it is in tension because we assume everything in tension first. Just the direction we show originally, everything is in tension, and that's the way that we want to usually assume. All 3 are in tension. All right. This is the first one. Okay. For the second one, we can say, so you have found TCD, this one, right? So for example, if you say summation of forces in y direction, does that make sense for you? If I say, if you say summation of forces about y direction, TKD is the only unknown in your equations, right? Because these two would be gone, so you know the other forces, so you can find the answer. So what I do, I would say, summation of forces in y direction equal to 0, this direction positive. So what do you have? You have this guy upward 56.7. You have a downward 20, right? You have a downward 30, right? So these two guys do not have any vertical components. And this TKD would be a downward, so TKD downward. And vertical component would be 3 over 3.6, right? You're going to use the vertical component on the triangle over the hypotenuse. Nothing else, equal to 0. From this, TKD would be equal to, all right, excuse me, 56.7 minus 20 minus 30 would be equal to 6.7, all right? So times 3.6 over 3 would be 8.04. But let me see if it is positive or negative. So if you bring it to the other side, it would be positive. Yeah, it would be positive. Because it's going to become positive, this side positive, all right. Okay. This is TKD. All right, any questions here? Okay. So the last one left would be TKS, right? TKS. So at this moment, the only thing left would be you can write horizontal summation of forces in x direction, really, because you know these two guys already. So you can find the third one unknown. All right. So let me do this here. Let's just, shall I? So let me do this. Let me write. So what I'm going to do, I'm going to keep the last writings of the answer for those two and erase the rest. So I would say, let's erase this one. So let's erase this one. All right. So if I write summation of force in x direction equal to 0, this direction positive. So what do you have? These three are vertical. This guy is horizontal, TKS. This guy has a horizontal component, you can say plus TKD. The horizontal would be horizontal side of the triangle over hypotenuse, plus TCD, nothing else, equal to 0. So here you have found TCD to be equal to 62.27. And TKD you have found to be 8.04 kilonewton, right? From this, TKS would be equal to negative 62.27 plus 8.04 times 2 over 3.6 would be 66.74 kilonewton, less than 0. So the member is under compression. All right. So these are the three asked for the method of sections. Any questions here? So I'm gonna give a break, like 5 minutes, but let's just finish the statics and then we go for the break and come back for mechanics of materials. I think that would be better. All right. So, so we went through the method of section. We solved everything requested. We just 3 members. Now method of joint is asked for HG and FG. So let's just solve it. So basically, I don't need any of this calculation. So if you do not mind, I'm going to erase these guys. I should have erased probably everything. because the only thing I need at this point really for method of joint there would be really this reaction 33.3. All right. Okay, so even I'm not cutting the member anymore. You're looking at the original structure. All right, so if you are asked to find the member HG and FG, actually, indeed, the method of joint is better because here the cutting wouldn't help you that much. Method of joint at point G would be the best way really to go because you're only dealing with two members connected to the joint. So method of joint would be much better way. So free body diagram of joint B, sorry, joint G. Okay, so usually the way that I would like to do it, I would like to just draw X and Y sort of like a direction for myself, show the joint G, right? Show like a portion of the members attached there. So you have one member like this, one member like this. Show all different forces applied to the system. So you have this reaction, 33.3. You have this internal force here, TGH. You have one internal force here, GF. Also, you also can show that infamous triangle, right? You can create a triangle. You can say 2 for this direction, 3 for the height. So 3.6 was right. 9 plus 4. Yes, 3.6 for the hypotenuse. All right. So you are set for method of joint. So you can say the summation of forces in X direction equal to 0, this direction positive. So what do you have? You have the negative TGF, all right? And also you have a negative TGH, horizontal, right, would be 2 over 3.6 equal to 0, right? From this, you can say TGF is equal to, so 2 over 3.6 would be 0.56. So you can say this equal to negative 0.56 TGH, all right? Also, we can say summation of force in Y direction, this direction equal to, this direction to be positive. So what do you have? You have at the vertical direction, you have TGH upward. So you can say TGH, the vertical side would be 3 over hypotenuse, 3.6 plus 33.3. This is this force. This force doesn't have any vertical component, so nothing else, equal to 0. From this, TGH would be equal to, so TGH would be 33.3 times 3.6 over 3. So it would be negative 39.96. So less than 0. So the member is under compression. Okay. So you can come back to this equation really here, right? So you can say TGF equal to negative 0.56 TGH, right? So TGH, here you have found to be negative 39.96. So it would be negative 0.56 times negative 39.96. It would be positive 22.38 kilonewton, more than 0. The member is under tension. All right. So you saw that. So what was the trick we learned here? If you are dealing with two members connected to a joint as unknown for you, you can go with the method of joint and that would be better. That would be quicker. The trick is two members on one joint. All right, questions? Okay, so let's move on. All right, so the next topic is a topic of centroid, center of mass, center of area, center of weight. So if our system is a discrete system, meaning that it is made of pieces that their shape is very well known to us. For example, a combination of triangle and rectangle, right? So just putting together like two rectangles, three rectangles to put together, right? The best way to find their center of mass, center of area, center of weight would be to follow these formulas, right? These three guys, X bar, Y bar, and Z bar of the centroid or center of weight can be found by summation of all the small discrete weights multiplied by their location, the centroid, the local centroid, over the summation of all the weights of the discrete members. For X, for Y, for Z. The only thing would be changed would be this local centroid would be changed in each of these equations. All right. So actually the better way to write this would be xi. If you add I here, that would be a little bit more making sense. All right. So let's just look at it. Okay. So this section is given to us, right? And we are trying to find its center of area. All right. How we can do that? So this is exactly what I told you, that all right, in this systems, when you know the geometry, it would be the best for you to go with these formulas that you would say X bar is equal to summation of X tilde I, in this case area AI, over summation of areas, and Y bar would be summation of Y tilde I's AI's over summation of AI's. All right. So I don't know, however deal it would be better for you. I would say let's just make like this. This to be one area for you, and this to be another area. So you have one and you have two. All right. So if I have something like this, how can I find the centroid? The X bar for this would be equal to, all right, so I'm going to call this one 1 and this one 2. All right. I can say it is X tilde 1 A1 plus X tilde 2 A2 over summation of areas A1 plus A2, correct? So it will be equal to what? All right, X tilde 1. X tilde means the centroid of this discrete area from the base. So it would be like the centroid would be this, right? The local centroid would be like at the middle of the rectangle, right? So what is the X of this from your base? Your base is like this Y-axis if you think about it, right? So the X of this point really would be the half of this guy, because half is the whole thickness. The half of half would be the distance from the Y-axis, which is really the X bar, X tilde I. All right. So this is your, I would say in a way like C1. And this point here is your C2, the local centroid for you. All right, let's write it. So your X tilde 1 would be half over 2, half inch over 2 times. The area would be what? The area would be 4 times half. All right, would be 4 would be the total, right? 4 and half, okay? Plus. Now for this second one, this is your X tilde, right? X tilde 2, right? How much is the X tilde 2? If you think about it, so first of all, let me separate the structure like this for you here. Okay, this is half, this is 4, right? The whole thing is 3. So how much is this? Tell me. Does that make sense for this to be like this dimension is? 2.5, right? It would be 2.5 because you half from that would be gone. And this height is half. Okay? So if I want to write for this part, the centroid is here, right? So this distance is how much? Does that make sense for if I say this distance would be, so half of 2.5 plus half, this half, right? Start from here. This half plus half of 2.5. Half plus 2.5 over 2, which would be what? 1.75. All right. So it would be 1.75. Let me just go with the red color. Multiply. And what is the area? The area of this one is 2.5 times half, right? Would be 1.25 square inches. Right? 1.25. Over the areas would be what? Would be 4 times half for this one, would be 2 square inches plus 1.25 square inches. All right. The x bar for this would be equal to all right. So the number I have found is 0.83. This is the location of x bar. Okay. What about the y bar? Y bar would be y tilde 1 a1 plus y tilde 2 a2 over a1 plus a2. All right. So this is your first member. This is your first member, right? This is a centroid. The y of that would be this much, right? It is 2. So 2 times the area of that, you already know that the area of this one you have found to be like 4 times half, which is 2 square inches. All right. So it is 2 square inches plus, okay. The y of this guy is this much, right? The y of this was, this one is a half, right? Times the area already you have found here, 1.25 square inches over summation of areas. Okay. From this, the y bar would be equal to, so it would be 2 times 2 plus half over half times 1.25 over 2 over 3.25. I have found 1.33. All right. This is x bar and y bar. So x bar here, y bar here. X bar you have found 0.83. For y bar you have found 1.25. Sorry, 1.33. 1.33. All right. Questions? All right. So let's move on. So moment of inertia, here are the formulas for you. And Here our parallel axis theorem. All right. So if you want to find the moment of inertia about x-axis here, you can find the moment of inertia about the centroid x prime plus the area of the cross section times dy squared, the y or the direction, the distance between two coordinate system, two axes of interest. Also, you can find the moment of inertia about y-axis to be the moment of inertia passing through the centroid plus area times now the x distance between the two axes of interest. Okay. So how we can use it? Let's just look at what we can be dealt with. All right. We are having a problem like this. So it says find the moment of inertia about the x-axis. If I want to find the moment of inertia about the x-axis, so it is a similar problem that is exactly the same cross-section we went through, right? It wants us to find the moment of inertia about this axis, x-axis. All right. So how we can solve this? Let me just draw the problem one more time. All right. This is your problem. And somebody might say, all right, why you keep assuming why you're separating from this region? Why you're not separating like with the horizontal line? So it is really up to you, whatever works for you better. Usually for the discrete shapes that it is known to us, you need to break it down into the more known geometries. So two rectangles for this problem would be making sense to cut. So either you can go with the one horizontal here, or you just go with the vertical way that I did. Up to you. All right. So if you want to find the moment of inertia about x-axis, how you can deal with this problem. Now you're having two figures. Again, for each of them, you need to detect their local centroid. Determine their local centroid. All right. Your total moment of inertia about x-axis, right, would be summation of their local moment of inertia plus a dy squared. Meaning what? Meaning for this figure, local moment of inertia about x-axis, meaning what? Meaning you need to find the moment of inertia about the x-axis, which is a horizontal axis. So would be what? Would be half times the height, which is 4 inch to the power of 3 over 12, bh third over 12, right? Plus the area half times 4 times dy squared, meaning that what is the difference between the axis passing through the centroid of this guy, which is this, right, and the axis of interest, which is this one. So how much is this distance? Tell me. It would be like half of 4, right? It would be 2 inches. 2 to the power of 2, AD squared. Okay. Plus, now we go to this small rectangle. For the small rectangle, you're gonna say again, what you are focusing on, you are focusing on the axis passing through the centroid of the second, the local figure that you are focusing right now. All right. So what is the moment of inertia about x double prime? It would be the other side, which is 2.5 multiply the side where the axis is perpendicular, which is half an inch to the power of 3 over 12 plus the area 2.5 times half. What is the distance? Now the distance would be this, right? The distance from your x double prime to x-axis, which is axis of interest for you, is half over 2, 125. Okay, so from this, your total Ix would be equal to half times 4 to the power of 3 over 12 plus half times 4 times 4 plus 2.5 times half to the power of 3 over 12 plus 2.5 times half times 0.25 squared. So I got 10.77 inch to the power of 4 for the moment of inertia about x-axis. All right. So this was the moment of inertia about x-axis. Sometimes you can be asked to find the moment of inertia about the axis passing through the centroid. For example, it can tell you what is this moment of inertia about this axis. The idea is the same. You need to find the local moment of inertia of the cross section plus AD squared. A would be the A, no problem. The D would be different now. The D, for example, in this case, would be the centroid of the local here, and this is your axis of inertia. So this height would be the dy. Okay, so make sure that what is requested from you, you're requested like an X or the axis passing through the total centroid of the cross section. So you can be dealt with that dy properly. All right, any questions here? Okay, so this is for our truss. Sorry, this is for our statics section. So let's just pause in at this moment and have like I would say it is good going for up to 310. 310 is good for everyone. Let's just go and a little bit just like freshening up and come back at 310 for the mechanics of materials. All right. Thank you, guys.